So good afternoon, everyone. Welcome to this new appointment for the 40 Under 40 lecture series on combustion. Today we have the pleasure to welcome Professor Francesca De Domenico. She's an assistant professor of sustainable aircraft propulsion at the Faculty of Aerospace Engineering of TU Delft. She completed her PhD at the University of Cambridge in 2019. Specializing in thermoacoustic combustion and laser diagnostics. And then she worked at KAUST, where she developed advanced laser diagnostics for reacting flows. She was afterwards a junior research fellow. She obtained a junior research fellowship at Gonville and Caius College in Cambridge, and where she conducted independent research in her postdoc. And since then, since joining the TU Delft lab in October 2022, she's been leading the Green Propulsion Lab, and she focuses on advancing sustainable propulsion technologies for aviation and power generation. So her research work involves experimental studies of hydrogen combustion, multi-fuel systems, and there is, of course, an emphasis on developing laser diagnostics tools. Today, she will talk about fuel flexibility on the path to zero emissions, harnessing multi-fuel combustion for aviation and beyond. We are very happy to have you for this series, and I give you the floor. Thank you, Francesca.
Thank you very much, Alessandro, for the introduction. And let me start sharing my screen. Share. Okay. Do you see it? All good?
Yes, all good.
Okay, perfect. Well, thanks a lot for the introduction. And again, welcome. My name is Francesca De Domenico, and I'm very happy to be here discussing the mainly experimental work that we've been doing here at TU Delft on multi-fuel combustion. That is, as I will explain during this talk, is something that we see as a necessary step towards getting zero emissions in aviation and also other energy applications. I'll start with giving let's see if it works. Okay, I'll start with the background, and sadly, this is probably the sad background slides that you've seen in many talks nowadays, which is, let's say, the catastrophic effect of climate change. So day by day, we really see, let's say, the terrible effect that climate change is having on our, let's say, on our society. And is really, let's say, we are probably reaching a tipping point in terms of let's say, the catastrophic effect that is now creating in the environment. And therefore, let's say, we are really, most of us in combustion, I believe, are really working towards, let's say, getting towards carbon neutral solutions, and, let's say, managing to reduce the impact of climate change in our society. Reduction of climate change effect in aviation and moving towards net zero is one of the core topics of research of the department, the Faculty of Aerospace Engineering at TU Delft, which is a city in the Netherlands, for who doesn't know that. And in particular, let's say, this is the core mission for which the chair of sustainable aircraft propulsion was created. So the our chair was, let's say, created 4 years back with a mission to pioneer cleaner, more efficient propulsion system that could dramatically reduce emissions and pave the way for sustainable zero carbon aviation. Now, I'll give still a bit of background for the background, and I'll dig a bit deeper within, let's say, net zero emissions in aviation, which is the topic I'm focusing my research on. Most likely you have seen a similar graphs many times. So these graphs show the, let's say, the carbon dioxide emissions from flights within the EU+ region, and this is the projection that we have from, let's say, from 2018 to 2050, taken from this report, Destination 2050 of EU. And what we see here, this is, let's say, what we see here is where the goal. So the goal will be for us to get at zero carbon dioxide emissions in 2050. And here are the solutions that are envisioned for the future. So not only improving technologies, but also operation, sustainable aviation fuels, and hydrogen. And hydrogen, as you can see from this projection, has a very big role in achieving this net zero in aviation. However, as you can see from this graph, we only see hydrogen being is added to the picture in the system from 2035. And the reason most of you already know, and I will further expand during the talk, but are really the different properties of hydrogen with respect to what we use today. So nowadays, we mainly fly using kerosene, jet A fuels types, and very small blend percentage of SAF. As I mentioned, we as combustion engineer, we mainly focus on the differences in properties within hydrogen and kerosene on a combustion point of view. But then there are really a lot of other problems that really are delaying the introduction of hydrogen within the aviation framework. Not only, let's say, storage and distribution in the aircraft, but also, let's say, making the necessary infrastructure available at the airport, also transporting hydrogen to the airport, and of course, ensuring that the hydrogen that we will use for aircrafts is produced in a clean and sustainable ways. So if we take all of this, we really see that there's still a bit of gap that we need to fill in order to be able to introduce hydrogen-powered aircraft in aviation in 2035. And if we take a look a bit at the numbers of the years, and we think that it might take 6 to 8 years to develop an aircraft that could fly with hydrogen, and other perhaps 8 to 10 years to develop the engine that can burn hydrogen in a safe and clean way, then we are really, let's say, lagging a bit behind with respect to this timeline in order to make sure that we could reach this goal here. So how can we make it this faster? How can we make sure that we are quicker to get to the introduction of hydrogen within aviation in order to reach the net zero goal in 2050? One way could be using some stopgap solution, such as multi-fuel combustion. And there it's the first time I introduce it, and I'd like to, let's say, explain the concept of this. So the idea of multi-fuel combustion is having a system that is synergically using kerosene as well as hydrogen in order to speed up the introduction of hydrogen within the aviation framework, while we mature our understanding of hydrogen combustion as well as the technologies that we need for having hydrogen delivered at the airport and carried on the airplanes. Having given this picture, I'd like to provide an outline of the talk. So the first part, with the first part of the talk, I'll go through, let's say, something that some of you might already know, but I'll recap, let's say, what are the differences in combustion properties between hydrogen and hydrocarbon fuels. Then, based on that, I'll introduce the multi-fuel combustion concept and how we are developing it here at TU Delft. And in particular, I will present the results of 2 burners that we are using. To be honest, it's the same baseline burner, but this will be clear later on. But so what I will discuss is how we are using multi-fuel combustion here at Delft, how we are developing systems. We started with a multi-fuel methane hydrogen burner, which we call HAPA burner, and then we retrofit this burner to also include kerosene into it within the project HOPE. Finally, I will discuss the next steps of the research here and of this implementation of multi-fuel combustion. And then I will provide some conclusions and outlook. Okay, let's start then. And okay, so here it's a small recap of what I discussed before. So how will the airplanes will look like in 2050? And this is providing just one possible scenario, because still we need to make the innovations that are necessary to introduce some of these planes. So what I want you to get as takeaway from this slide is that in 2050, if we want to decarbonize, we will see different shapes, different size of planes based on the emissions that we will have. And we see that hydrogen has most likely a very big importance in the decarbonization of the short to medium range aircrafts, while we keep sustainable aviation fuels only for the big range. Now, another thing that I'd like to point out from this scenario is that sustainable aviation fuels are the only one that we could potentially use in the current airplanes. But batteries, fuel cell, and hydrogen combustion are still planes that need to be developed. So there's quite still a lot of road and a lot of discoveries and technological advancement that needs to be made in order for us to get there. So one might wonder, okay, why hydrogen then? Why would you just not stop with the kerosene or sustainable aviation fuels if it's so difficult? But the reason behind that is that we simply cannot just use sustainable aviation fuels for decarbonization. Hydrogen has an enormous potential to decarbonize the aviation system. First of the aviation environment. First of all, it has zero emission potential and allows for long-term sustainability. It has unique properties, being extremely light and has a very big amount of energy per unit mass. It can be versatile in a versatile way. It can be used in different propulsion systems, and it is available in nature, which means that as we are developing the systems for producing hydrogen, the cost of production of hydrogen will decline, while instead for producing sustainable aviation fuels, there is either not enough feedstock material or base material that can be used to make them, or conversely, the cost of production are extremely high that we cannot think to use them for fully decarbonizing all the aviation sector. So from this, so it clearly emerges that it is really offering a transformative way for the aviation. However, there are still big challenges that we need to manage in combustion dynamics, which is what we study, storage, infrastructure, and safety. Now, on the point of view of combustion, hydrogen, we cannot really consider it as a drop-in fuels. In fact, has very different properties with respect to hydrocarbons. And I'll be quick on this because you probably have seen this many times, but it is much lighter with respect to hydrocarbons, both methane and kerosene, much higher flammability limits, much faster flame speed, and relatively higher adiabatic flame temperature, which really creating some obstacles because the, higher diffusivity and reactivity is, making it hydrogen flames more prone to flame instabilities. Higher flame speed means a higher risk of flashback, which is detrimental if you think about an aviation engine where you want to be safe 100%. And also the higher flame temperature might increase the amount of NOx that is produced, which is something that we don't want, because we don't want to resolve the CO2 problem and then getting into, having high NOx problems. So with all of this, let's say we see that there's quite a lot of work for us in order to bring hydrogen within the aviation sector in let's say in a suitable way to have safe, green, and efficient airplanes. And multi-fuel combustion can really act here as a stopgap solution to speed up the introduction of hydrogen within aviation. In fact, if you can use simultaneously both hydrogen and kerosene, this system would allow you to have is more flexible. So it really gives you the flexibility of being able to use both hydrogen and hydrocarbons within the various applications. It has a higher adaptability, meaning that you can think about retrofitting the current engines with adding the hydrogen lines rather than fully redeveloping the engine for only hydrogen-only solutions. It will, of course, have the benefits of reducing the emissions, not only carbon dioxide, but also NOx and soot, as I will show later on. And then it can really ensure that there's a security of supply, because you don't really rely on hydrogen only, which might not be available at the airport where you land. And also it's cost effective, because if you are not forced to use 100% hydrogen, in the moment in which hydrogen, let's say still the cost, still infrastructure is being developed, the use of diverse fuels is helping to reduce the dependency on expensive or scarce options. So we really see multi-fuel as really a stopgap solution towards the zero emissions, which will allow to adopt hydrogen while support the decarbonization goals, both for aviations and land-based power applications. Now, for here, I'd like to make a bit of a distinction within the two, because we know that, let's say, in terms of, like, say, power plants, gas turbines, land-based, there's been already quite some developments in terms of, like, hydrogen turbines. And the issue here, which is really where our research goes, is like towards aviation, because the level of safety and the requirements in terms of space as well as, let's say, geometrical constraints in aviation are much higher than with respect to what is, let's say, asked for, let's say, land-based applications. And therefore, really, the aviation sector is the one where, let's say, further research is needed for this, for let's say, safely introducing hydrogen within the engines. So, of course, let's say there's been some previous work on multi-fuel combustion in hydrogen and kerosene. As I mentioned, we are looking at application for aviations, and therefore, let's say, kerosene is the other fuel with which hydrogen would work. But overall, relatively, there has been not that much interest, really, because hydrogen was never really put as a fuel in the picture as a fuel that could be used for aviation. So if we do take a look at the literature and at what happened, with the previous studies that were done on multi-fuel system that could work synergically within hydrogen and kerosene, the first experiment that we found is an experiment in the 80s that was done by Hiro Yashu in Japan, in which he developed a hybrid fuel nozzle that could use liquid kerosene together with gaseous hydrogen, going from 100% hydrogen to 100% kerosene. Then there have been some studies on lean premix prevaporized kerosene with hydrogen, which means that kerosene is not sprayed as it would happen in aero engine, but is, let's say, before pre-vaporized and then injected in the chamber and then mixed with the hydrogen. And this, of course, let's say, has some benefits, because it means that both fuels are gaseous and the combustion is slightly more easy to deal with rather than having two-phase fuels. And finally, there is also the leaf burner, which was developed in ETH Zurich, which can run both at hydrogen and kerosene and with a mixture of two, but it really requires, it is not a conventional design. So it's a novel combustion concept where, let's say, there's a different system in terms of injection. So while experimental work is quite scarce, there's some work that could be found in terms of CFD simulations that are studying at how hydrogen and kerosene would interact within each other, and also some chemical reactor network that are analyzing the properties of multi-fuel system hydrogen kerosene. And this is, let's say, all the literature up until 2020. But recently, there's quite a bit more interest in multi-fuel combustion, really for this idea of for the potential that multi-fuel combustion offers in terms of, let's say, key enablers for the advent of hydrogen in aviation. Here I listed, let's say, 3 of the main, let's say, projects that are now running on this, or that I'm aware of. There is a clean aviation project that is looking at, let's say, the introduction of hydrogen within aviation, and they aim to, let's say, develop and test a multi-fuel aircraft engine, which Fokker would like to fly by 2035. Fokker is an aircraft company that Dutch-based that has pledged to fly a multi-fuel plane by 2035. And Derwent Technology is a British-based company which is developing a multi-fuel hydrogen kerosene burner for narrow body. And this has all happened after 2020. So really recent interest within with this concept of multi-fuel. And within this project, I'd really like to highlight the project HOPE we are working on. So HOPE is a project we are working here at TU Delft, and HOPE stands for Hydrogen Optimized Multi-Fuel Propulsion System for Clean and Silent Aircraft. It's a Horizon Europe project that was funded in 2022, so in a call towards a silent and ultra-low local air pollution aircraft. And for HOPE, we aim here to develop a novel aircraft, which is as a multi-fuel ultra-high bypass ratio turbofan engine. So the multi-fuel aircraft I've been talking about, then where the kerosene is stored within the wings, and the hydrogen is stored at the tail. The objectives of this project is to demonstrate at low TRL level, so TRL 1 to 4, the feasibility of this aircraft and its capability to reduce at landing and takeoff not only carbon dioxide emissions by using simultaneously hydrogen and kerosene, but also NOx, carbon monoxide, soot, and noise. Overall, by having a reduction of climate impact of 30% with respect of the baseline A320neo that is used as a baseline aircraft. And this is the consortium we're working on. So it's a European project, TU Delft is leading, and then 6 partners across Europe are collaborating with us within this project. As I mentioned, at TU Delft, we are really focusing on the development of the multi-fuel ultra-high bypass ratio turbofan engine, and in particular to demonstrate the advantages of multi-fuel combustion in our lab. Now, before coming into what we are doing, I'd like to provide a bit more of a context of what are the advantages of multi-fuel combustion in terms of combustion properties. So previous studies demonstrated that not only you reduce carbon dioxide, you also reduce CO, soot, and thermoacoustic instabilities. And you, by adding hydrogen to kerosene, you alter the NOx pathways with the potential reduction of NOx. Furthermore, you reduce the lean extinction limit and ignition time delay, and also increase the overall reaction rate. And finally, because you don't have to carry all the hydrogen, you also have the benefit of reducing the hydrogen tank size, which is advantageous because it means that you don't have to fully change the shape of the airplanes. But the issue with that is that while all of this was mainly demonstrated from other CFD of chemical reaction network investigation, there is really lack of experimental investigations on multi-fuel systems that are suitable for aviation. And that's where really our research comes in. So our goal is to efficiently combine hydrogen and kerosene to boost the performance while minimizing the emissions. And this will do it experimentally. So we want to develop a system in the lab that with which we are able to investigate and understand dynamics of hydrogen and hydrocarbon blends, the advanced diagnostics technique for multi-fuel combustion, which is extremely important considering the complexity of the physics and of the flows that are involved, the practical implementation in aviation. So also provide a roadmap for introducing such a technologies within in the aviation sector. Now, after this introduction of the system, I'd like to bring you to the lab and really show you how we are tackling the problem with the two burners that I discussed previously. And I'll start with the Swir stabilized hydrogen methane burner. Two reasons: a bit historically, because this is the first burner with Swir stabilized burner that we tested with hydrogen, but also because this is really the baseline burner that then we will modify. We have modified for the addition of kerosene. So here a picture of the burner, and here how the experiment looks like, the flame looks like. So what you're seeing here is an hydrogen flame the hydrogen flame that is burning in the chamber, and most likely we are shining the wedge PLIF laser into it. You might see it. You might see it a bit. You might have seen it on the flame. And so here as diagnostics that we make on this flame, we have a high-speed PIV, we have OH and NO PLIF, and of course chemiluminescence and the visual images on the flame, as well as an exhaust gas analyzer and a far-field microphone to measure the acoustic signature of the system. Now, a bit more about the injection strategy, because as most of you that work in the lab know, it is very difficult to stabilize both a hydrogen and a methane flame on the same injector from the very difference in the very different flame speed that the two have. And therefore, I'd like to show you how we do it in our burner. So first of all, as I mentioned, is a Swir stabilized combustor. So we have an axial swirler that is like feeding, going into the combustion chamber. And what happens is that, let's say, if you have a sufficient highly Swir number, then you generate this flow pattern with an inner recirculation zone here, and two outer recirculations a toroidal outer recirculation zone here on the side, with a stagnation point here. In our case, the system is practically premixed or technically premixed, meaning that we do not have fuel and oxidizer mixing in the swirler, but for safety reason, we try to inject fuel as late as possible, but early enough in order to still have a decent level of mixiness of the fuel within the combustion chamber. And therefore, we inject the fuel right downstream of the swirler, as you can see here, and it corresponds to this 4 injection port here on the swirler design. If it was a methane flame, for the methane flame, let's say the methane flame would nicely sit and stabilize there, as you see it here. So it's let's say we would most likely we do not in fact encounter problems of flashback in most of the cases. However, what happens is that when you have hydrogen, because hydrogen has a much higher laminar burning velocity, then 100% or most likely the flame would flash back within the injector. And in order to avoid the flashback, what we use is the concept of axial air injection that was introduced in 2015 at TU Berlin, which means that there is a central jet of axial air injection that is used to compensate the actual velocity deficit generated by the high burning velocity of the hydrogen. And this axial air injection manages to push the flame downstreams and stabilize it, the hydrogen flames, avoiding flashback. And this corresponds to the central jet of air here that you see in the injector. Here, I briefly summarize the experimental conditions. So not without going too much into details, this is a 12 kilowatt burner, at least in terms of, let's say, design point. And we keep the mass flow of air constant while we change the share of hydrogen. So what happens is that by keeping the power and the mass flow of air constant, by changing the percentage of hydrogen, we slightly change the bulk velocity as well as the equivalence ratio. In terms of power that we investigate within our analysis, mainly we tested the burner from 8 to 14 kilowatts, and we have two swirlers with the two different swirl numbers. But for the results I'm going to show now, the swirl number that we use is the one with the swirl number 1.1. Now here, it's how the flame looks like, going from 100% methane, so this flame here, to 100% hydrogen, which is the flame here. And as you can expect from my previous description, and because of the much faster laminar flame speed of hydrogen, you see that the flame is getting closer. The more we had hydrogen, the closer the flame gets to the injector and the more compact it gets. If we take a look at the stability map of this burner, we see that the axial air injection helps us to achieve continuous operation from 100% methane, which is, let's say, here represented here in this stability map, to 100% hydrogen, which is here on this stability map. While instead, if we do not use axial air injection, as anticipated, it is not possible to achieve a stable combustion from 100% methane to 100% hydrogen, but we at equivalence ratio 0.6, the flame let's say multi-fuel flames starts flashback. Then, okay, of course, this is a big advantage to be able to use the same injector burner for two different flames with two different fuels. But of course, this has some drawback, and this could be seen here in the OH star chemiluminescence data and high-speed PIV data that were taken. Without going into all these cases, I'd like to point out that the flow, let's say, from the streamlines, you can see that the flame at 100% methane is as a nice, the nicest swirl structure that you'd expect. You see here the outer recirculation zone and the inner recirculation zone. But the more we had hydrogen, the more we start losing the inner recirculation zone up until at a percentage of hydrogen of 80%. We do not have anymore this inner recirculation zone, and at 100% hydrogen, the flame is mainly behaving as a jet flame and not really anymore as a swirl stabilized flame. So we keep the outer recirculation zone, but we miss the inner recirculation zone within this system. So if we do take a look at let's say, the two extreme case, so 100% methane without axial air injection, we do see a nice swirling flame, both from the PLIF images as well as from the PIV. Well, instead, from 100% hydrogen, of course, the flame, as anticipated, as more the, let's say, shape of a sort of jet flame with respect to, let's say, a nicely swirl stabilized flame. And what we do see is that also the NOx, which is one of the main issues, as I mentioned, for hydrogen, is very different. Indeed, for the methane flame, we have as expected, let's say, production of NOx both in the inner and in the outer recirculation zone, while instead for the hydrogen flames, the inner recirculation zone is not there anymore, but we have a much higher production of hydrogen within the high outer recirculation zone. So overall, if we take a look at a scan, overall, let's say that we can say that axial air injection is degrading the swirling motion of the flow and the fuel air mixing, so it eventually results in higher NOx emissions, which we can see here. So of course, if we take measurements from the exhaust gas analyzer, we see that by increasing the hydrogen mole fraction, the amount of carbon dioxide reduces up until we don't have it anymore when we have zero hydrogen zero methane in the mixture. However, the NO measured in the gas analyzer tends to increase, which is of course something we don't want. However, from these graphs, from these results, still or in particular from the exhaust gas analyzer, we really cannot capture very well how is both the accelerator injection as well hydrogen additions are acting with the NOx emissions, because those are two different phenomena. The first one is a let's say a non-swirling flow within the swirler, and the other one is instead, let's say, the use of the addition of hydrogen, which burns at much higher temperature, and therefore, let's say, is making the system more prone to, let's say, producing thermal NOx. So what we did is, let's say, we went to the lab and we did, let's say, 3 campaigns to take a look at what are the effects of both accelerator injection and hydrogen on the NOx emissions of the burner. In the first test, we kept all the quantities constant, and we only started increasing the accelerator injection in the system. You can see here the PLIF and the NO PLIF and the OH PLIF results that we got from the burner. And you can see that by increasing the content of accelerator injection from the NO PLIF, so we go here from 0% accelerator injection to 20% accelerator injection, we start having, let's say, a bigger, let's say a higher production of NO in the outer recirculation zone. And this is basically telling us from the data that the accelerator injection is increasing the overall NO emissions by decreasing the mixing quality, meaning that the fuel and oxidizer are mixing worse within the mixing tube, and therefore this corresponds in a higher NOx level within produced by the burner. The second test that we did was increasing the content of hydrogen by keeping the power and the accelerator injection constant. And here we can clearly see, so here we have a flame with 0% hydrogen, here a flame with the 25% hydrogen, and here a flame with the 40% hydrogen, and without having accelerator injection. And we can see that without accelerator injection, as expected, by increasing the hydrogen percentage, this leads to an increase in the overall NO. In particular, this is mainly due to the higher thermal NO that is produced. And the final test that we did was increasing let's say still increasing the percentage of hydrogen, but in this case with accelerator injections at 20. And we see that in this case, there is a bit of nonlinear behavior. Here we have 40, 60, and 80% hydrogen. And overall, the amount of NO that is produced in the case of 80% hydrogen is higher with respect to the amount of NO that is produced with 100% hydrogen. Initially, this was a bit puzzling, but then I think that's how we let's say understand this, is that if we look at the cases here, so if we go back to the test matrix, here we were in the case of 80% hydrogen, we were at an equivalence ratio of 0.68. In the case with 100% hydrogen, we have an equivalence ratio of 0.62. And therefore, if we look at the NO emissions in this graph here, it's not really exactly the same conditions, but I think it kind of like can be used for explaining this. We are really, not yet, let's say, we are going in a region where the production of thermal NOx is not yet that high. And therefore, this drastic drop in equivalence ratio within the two cases is really creating this big change within the let's say NO that is produced. So the main takeaway that we could take from these results is that really what we see is that as expected, one, let's say, system that is partially premixed or technically premixed might not have a good mixing, and in particular, axial air injection requires, let's say, requires some further investigations of how the dynamics of how the mixing in the mixing tube is occurring, in order to improve the mixing within the fuel air and obtain an uniform fuel. So to investigate this, I'll be brief in this experiment, but I would just like to point out that we are, let's say, doing some non-reacting experiments in a sort of what we call a plastic twin of our rig. So it's the 3D printed version of our rig, when we can change most of the parameters of the injection system quite quickly. And basically what we are doing is we are taking a look at the mixing here in the mixing tube. We have now a transparent mixing tube, which is this small rectangle that you see here, let's say it's less than 4 centimeters, so it's quite in height, so it's quite small. And we are taking a look at how the hydrogen and the air mix. In this case, we don't use, of course, hydrogen, but we are using helium. And what we see here, this is how some results that we get, where, let's say, for the sake of time, I won't really go that much into details, but here you can think that these particles represent the seeded part represents the fuel, and the unseeded part represents the air. And we can see that within such a configuration, we do not, also from the LES, we do not have a very good mixing within the fuel and the oxidizer. But if we instead we improve the design, and in particular in this case, what we improve is the momentum of injection of the fuel with respect to the air, then we can have a much more uniform and better mixing of the fuel and the oxidizer within the mixing tube. And now we'll, of course, from this non-reactive experiment, what we'd like to do is to go in the lab and test whether that's actually the case. Now, I think this concludes, this provides also, let's say, a bit of further development for this methane hydrogen experiment. And now I'd like to go to actually what is the real, let's say, core work of this for the aviation system. So it's the, let's say, the kerosene addition to this setup, or what we call hydrogen system combustion of kerosene, which is really the goal of the Project HOPE. And of course, we are talking about something quite different, because while hydrogen and methane, as different as they are, they're still in gaseous form, and they're not much different one with respect to the other. But when we start talking about hydrogen and kerosene, there's a big difference, not only in volume, but also on the only and mainly in the fact that we are talking about a liquid system, so the kerosene spray, and a gaseous system, so the hydrogen. And for doing this, for developing the system, how we are proceeding is that we are doing a sort of a simultaneous experimental and CFD-based scouting for the design of this multi-fuel kerosene hydrogen atmospheric burner. Because we're doing it with numerical people, it was strongly advised to us that we use the pressure-based atomizer. So those are simplex atomizer for the kerosene that we want to use to spray the kerosene within the system. And here the results, let's say here, the free injection configuration that we considered by keeping the hydrogen burner as baseline. So the hydrogen burner was discussed before as baseline. As I mentioned, there are 3 injection configuration of the kerosene that we are considering. The first injection configuration, let's say, leaves the hydrogen injector as it is, and is adding 2 kerosene sprays here on the base plate, far from the mixing tube, as far as, let's say, we could fit them in within the plate. The second injection configuration was, let's say, we looked at was to add the kerosene, spray the kerosene in the mixing tube downstream after the hydrogen. And the third injection configuration that we consider is a full redesign of the system, where we change we remove the auxiliary injection channel, but we add the kerosene sprayed at the center, and then we have the hydrogen that is still, let's say, injected on the side of the swirler. So it's a full redesign. To start with, because we are working together with this company in Italy, Ergon, which is doing the CFD scouting for this project, we decided to start testing the injection configuration 1 because it allowed us to just retrofit the burner that we had. So if you remember, this is the design of the hydrogen burner that we had. And here it's how let's say, the burner looks like when we put the 2 kerosene injector on the side. Reason why we have 2 is because of power split constraints. We could not go to lower flow rates in the injector to allow for 4. So we could only use 2 of those. And that's how the first experiment that we did on this system looks like. So we started we started looking at, let's say, looking at the flame and taking the, let's say, the sound measures with a far field microphone. And here I have a video that shows the transition of the flame from the 100% hydrogen flame, which is the one that you saw before, to the 100% kerosene that, well, you haven't seen yet, at a power of 9 kilowatt. From the video, you see that we start adding the kerosene, and slowly you see, let's say, more and more, let's say, strips, let's say, of kerosene that starts getting burnt, up until clearly you start having let's say, all the kerosene flames, because in the meantime, let's say, we have dropped the hydrogen content. So to clarify this, in this video, we start from the hydrogen flame, and then at the end, we get to the 100% kerosene flame, and you saw all the transition. Rather than going in transient, we can take a look at the, let's say, steady state, where we, let's say, we go from let's say, we have these 5 flames for different power split. So this flame here is the 100% hydrogen you saw before. This flame here is the 100% kerosene that with, of course, by having the 2 sprays injector here, is resulting in these 2 lobed flames. And then those are the flames here are the one in between, where we are let's say, calling them by the power split within hydrogen and kerosene, all at a power of 9 kilowatt and a nominal equivalence ratio of 0.4. If we want to take a look at this data, what are these telling us? So of course, the flame is different, very different. When we have hydrogen, we don't have droplet combustion. When we have kerosene, we start seeing the effect of the droplets, and the flame topology changes quite a bit by adding kerosene. The flame gets larger and larger and larger up until it becomes it starts having these 2 lobes here. And this can be explained by, if we do take a look at the combination of the timescales, chemical timescale, evaporation timescale, and mixing timescales. Also, the size of the flame is different, which could be directly related to the different flame speed within hydrogen and kerosene. And also we see, let's say, of course, a soot formation within the system from one to the other. Finally, here, another effect that we observed, and I could play the sound, but I will not, because I think it's quite unpleasant, is that with the pure hydrogen, sorry, I'll go back a bit, with the pure hydrogen and pure kerosene case, we see a tone of 300 Hertz appearing, and this 300 Hertz really corresponds to the natural frequency of the chamber. So somewhat both the hydrogen and the kerosene flames are exciting the natural frequency of the chamber. But when we start having hydrogen kerosene blends, we see that the effect of multi-fuel is really reducing the let's say, the height of this peak, and therefore is really reducing reducing the, let's say, let's call it, I'm not sure if it's a really thermoacoustic oscillation, but this strong tonal noise that was observed before. Now, of course, with this flame, we know that this is does not really look as a practical system that one can put in aero engines. Nevertheless, is really helping us to, let's say, really was good to provide the, let's say, the Ergon with a good test case to test their model. They are using RANS, a K omega shear stress transport, and eddy dissipation concept based on a partially stirred reactor to model the multi-fuel hydrogen kerosene system. And here you can see that even by using the RANS, they were quite able to capture the average heat release rate and overall the flame shape that we had within the various cases from 100% hydrogen to 100% kerosene. As a reminder, what we're trying to do here is to develop a system that is suitable for multi-fuel combustion of hydrogen kerosene, and therefore the use of RANS is also good for let's say scouting quickly and analyzing quickly several conditions rather than going to more, let's say, computationally heavy simulations, which will require way more resources and way more computational time. So if we go back to this idea of scouting, then if we see the, let's say, this is the injector that we just tested, and we can see the, let's say, the free cases. So that the free cases I showed, the kerosene only case, the multi-fuel case, hydrogen and kerosene, and the hydrogen only case by showing, and here I'm showing the velocity and the temperature field. This really very well matches with what we saw in the experiment. Meaning that in this configuration, we do not really obtain a uniform distribution of the fuel. The time for evaporation mixing of the kerosene is not sufficient, and therefore there's formation in the kerosene flame of fuel-rich spots, which eventually leads to high level of NOx. However, in the moment in which with the same let's say computational infrastructure, our colleagues at Ergon tested the injector free, what we see is a very different flame, both by looking at the velocity fields and at the temperature field. And what we see is that the kerosene only multi-fuel case and hydrogen only system, they really do not differ that much in terms of like neither the velocity field or the temperature field, which is something that is we are seeking, meaning to have a system that is producing with hydrogen, kerosene, or in between, a flame that is as similar as flames that are as similar as possible one with each other. So we see that from the RANS, we see that the kerosene plane is surrounded very well by the swirling flow. There are less peaks of high temperature, so there's not really that much. There are really little high temperature zones while instead with the previous injector that we tested, there are much higher, much bigger peaks of hot temperatures. Also, we see that the hydrogen addition is a bit decreasing the size of the kerosene's hotspots. And overall, therefore, from the RANS, we see that the hydrogen addition is reducing the NOx emissions. This was only done by RANS, and now we are really about to start testing this concept in the lab. And I hope that soon will come positive results that corroborate what was observed numerically. Finally, I'd like to, let's say, provide some, share something about what else we are doing and what are the next steps for this work. So first of all, of course, we are, first of all, is diagnostic development for these systems. We have a system that is complex because it's multi-phase, multiple species are involved and multiple timescales. Flows are highly turbulent, and we are looking at high temperature and eventually high pressure environments. So of course, we want to measure velocity fields, but also scalar fields. And beyond the OH and NO measurements that you saw within these slides, we are also working in developing spray imaging for the droplet part of of the multi-fuel combustor to look at size and distribution. And also we are interested in developing cars and the leaks for simultaneous temperature, speed of sound measurement for the temperature map of the combustors. Briefly, what's next then for this project? So now we are working on improving the injector. Then we aim to also, let's say, go to high power. This is a preliminary testing of a burner with let's say that we aim to bring to 100 kilowatts. And also we are working on developing a small pressurized vessel that could go up to 5 bar, in which we could test what happens at pressure to this system. With the hope that finally we'll be able to provide, let's say, to see really such a system flying within a novel multi-fuel hydrogen aircraft. So to conclude let's say, I strongly believe that hydrogen can drive a paradigm shift in combustion, offering a unique opportunity to rethink and innovate within our combustion system. But in order to unlock its full potential, we still need further knowledge of the combustion properties to ensure that it's safe and effective to use. So in order to stop the gap, we can use multi-fuel combustion system, which can enable a practical and flexible pathways to decarbonize the energy sector. And beyond that, also synergically using various fuels can really help leveraging the best attributes of the various fuels and optimizing the system's performance across the various range of applications. And because we are really working on the redeveloping combustion system, canonical experiment, a lab experiment really offer the possibility of, let's say, developing and testing novel solutions for future innovations, and can offer insights and address current challenges. To conclude, I'd like to acknowledge all the people that worked in this experiment. Of course, we all know that experiments take a lot of time and effort from everyone. So there's really big group of people that have been working within the combustion chair, not only, let's say, academics, but also, let's say, technical staff, PhDs, postdocs, and master students. And here the main name of PhDs and master student that worked on the various experiments: Lorenzo Palanti and Lorenzo Massei from Ergon from the RANS, and Professor Arvind Ganguly Rao, who is the chair of this, let's say, of the Sustainable Aircraft Propulsion, and has been, let's say, very much involved and let's say bringing in many ideas within these projects. And this I conclude, and I thank you for your attention and for the opportunity to share our work.
Thank you very much. Thank you very much for this very nice talk. There is time for question. I would like to invite anyone who has questions in the attendance to raise the hand, unmute himself or herself, and then ask the question. See who is the first.
I can break the be the icebreaker if you want me to.
Yeah, please.
I can. Thank you. Thanks a lot, Francesca, for this very nice talk. I have a question regarding the experiment of hydrogen and kerosene, because you showed in the previous in the early slides, you talk about you gave an introduction, you talk about the lean premixed pre-vaporized system, and I was wondering why did you not choose this system to study kerosene and hydrogen combustion, but you chose to have a kerosene spray in your rig?
I think it's not really realistic. Some people think, but we don't think so, that there will be a pre-vaporized system for aviation. So an aviation injector will be sprayed. So that's why for this specific case, we started with looking at spray plus display plus hydrogen. We are developing a burner for premix pre-vaporized, but then the practical, let's say, what we would like to get out of this is not really the, let's say, is not really the behavior, because it will be perfect. Let's say if you premix pre-vaporize, then you'll have a much better mixing. Then you really are able to see, let's say, get a reduction of NOx, soot, etc. But we want to see more in a practical system, which is something that not that can fly, but similar to something that can fly, how this will work, and how close can we go by using a multi-fuel, multi-phase system to a ideal system, which is the lean premix pre-vaporized.
Okay. Thanks, Sophie. Yeah, it's a reason of the being still grounded to what industry has been using so far, and implementing like kind of step-by-step changes to existing combustion technologies. Okay, thank you.
So we are working on that, but I think, as I mentioned, let's say it's really the practical side of saying if the current engines use spray system and pre-vaporize won't happen, how can we use, how can we get good properties still using something that is similar to what's flying?
Okay.
Thank you. There is a question. I think it's written in the chat. So I was wondering if you could give more details about the numerical settings you used, especially for the combustion modeling. I imagine the refers to the closure that you use.
Okay, as I mentioned, is the combustion model is not ours, so I'm not, let's say, 100% familiar with this. There's a paper that should be available online where this is fully well described, and they describe the meshing, etc. What I know, let's say, from their simulation, that the biggest challenge is to, let's say, really describe the combustion process when you have two streams of fuels that are totally different. And for this, let's say, it was this, let's say, this kind of, let's say, this approach that Ergon used was chosen. But I would really recommend to go to the paper that it was published, was presented at ICAS conference in September. And I think you will be able to find it online on the TU Delft repository.
So I don't know if there is any other question. If not, maybe I'll would like to thank you again, Francesca, for the very, very nice presentation. I would like to thank all the people who attended this presentation, and I'll give you rendezvous to the next appointment of the series. Thank you very much.
Thank you very much.
Bye.
Thank you.
Bye-bye.